My name is Mathias Gaunard. I am French, but I work here in the UK in London. And I'm going to talk to you today about optimizing software, and in particular optimizing software for the hardware that we have, making sure that we make good use of the special features that modern CPUs might have. So just over to who I am. I work in finance in low latency trading. Which is very performance sensitive. But before, I'd also worked on other kinds of performance sensitive programs like numerical simulations. And what I found quite interesting is that low latency world is very different from numerical computing, and we care about vastly different things. So a lot of what I will be talking about is more applicable to numerical computing software, but there are a few things as well which I have found useful when designing a low latency trading system. So let's look at the program. Yeah, you can still see things beside me that being gray. So the first part of this talk, I will be talking about how hardware actually works, because I think that to optimize software, you need to understand the hardware. And then based on all of these features we've seen in the hardware, we'll see what you can do from the software side to make sure that your software better maps to how the hardware works. When we think about optimization, what do we mean? We mean about a program that performs better. But performing better means different things to different people. Sometimes you care about throughput, sometimes you care about latency. Sometimes you just want to use less resources. You don't really care much about the speed. You just want something that uses less memory. So you want to optimize for different things, but in any case, regardless of what you want to optimize for, having a good understanding of the hardware will help you. So just to give some example, so in low latency trading, what we do is we receive a packet from the network, we look at it, and if it's interesting, we send another packet on the network. So what we care about is the speed between when you receive the packet and when you send the packet. But when you're doing a big simulation, it doesn't really matter the speed between when you deal with that one step and another step. You can be delayed in the past. All that matters is that you can process a big chunk of data in a certain amount of time. And so in this case, you will optimize more for throughput, for being able to deal with a stream of data, many different. Not just one event, but multiple events, and you want average speed rather than the speed of a single event. So about optimization, a lot of people talk about it. We've had many talks about it in the past, here in ACCU, at many other conferences. So I don't think I will be telling you anything revolutionary. I don't think I have all the answers either to all your problems. Doing optimization is very nasty and dangerous business. You might think that you understand how the hardware works and you can make it faster, but that's not always the case. You should measure things, but measuring things is its own problem. So I won't be talking about measurement at all in this presentation, but just be very careful if you want to engage into optimization. So I'll talk about this a little bit already. So I'm not going to. We only have 90 minutes is still a fair amount of time. It will only look at all the possible things, but we will not go in depth into optimizing everything with all the possibilities of optimization you can do, just giving a list of different optimization that might be interesting to do because of certain ways things are implemented on the hardware level. As I said, don't over-engineer. You might be tempted because you know that the CPU works in a certain way, that you should spend a lot of time doing it very carefully, but usually compilers are fairly smart. Your CPU is also fairly smart at reinterpreting your code. So only do it for fun because you find it interesting, which is also part of the reason why I personally do it, or because you've seen that there is a need to do so. So we'll look first at the hardware, like I said. What's interesting is that modern hardware like x86 actually does a lot of things to speed up your code. It doesn't just dumbly take your instruction and interpret them one at a time. It's basically a JIT compiler which will reinterpret your code and reorder things and do many things to already optimize them. So we'll try to understand a little bit what it does. And then I will show a number of tricks, or well-known techniques that you can use to optimize. So I'll be talking about C++, but most of the talk is language agnostic. So what happens typically when you write some C++ is that you have the source code in C++, which is first mapped to an intermediate representation of the compiler, and this is then mapped by the compiler to machine code, and the machine code itself, which is targeting a specific architecture like x86, will be reinterpreted by the machine to be translated to a specific set of micro-operations which depend on the microarchitecture. So, for example, as well and Sandy Bridge will do different things, reinterpret differently your assembly to execute it more efficiently. So, of course, I think it's already hard to understand what happens in a complex C++ program. If you try to read compiler IR, it's much more difficult to read and understand. Assembly is very difficult. And so you're not going to go down all the steps. But it's important to know that every time there is a big abstraction between all of those layers, and big transformations can actually happen. So just to show what is assembly, maybe some people haven't been exposed much to that sort of thing. So assembly is a list of instructions which are executed in order. So that gives you illusion at least that you execute the first one and then the second one in the list. And you can have jumps, which will go to a given address. So actually, all of the instructions also have addresses in memory, and so you can have jumps. So this is, for example, some relatively silly C++, which I wrote trying to get a fairly obvious mapping between the C++ and the assembly. And we can see that for a given function, what gets generated is a piece of code which starts at a given place. So just the name is used as a memory address. And we can see, well, this code starts by doing a comparison of B by 2. So A and B are going to be stored in ESI and EDI, respectively, which has registers. And so the compiler you can see, did a conversion. Instead of comparing it to 2, it compares to 1. And then well, regardless, it will copy into EAX the value of A. And if BE being less or equal, if the result of the comparison is less or equal, it jumps to L2 and it returns. So I mean, it will return here. But otherwise, it will carry on. And we can see it's adding 1 to ESI, which was 2. So everything relatively makes relatively sense. There's a bit of weird stuff because the div instruction is a long division, so it needs to XOR one register to set it to 0. But otherwise, there's a fairly clear mapping between the C++ code. So a loop does a comparison here at the end, right? So ECX being B plus 1, and so it compares this, and if the condition is not satisfied, it goes back to this address and carries on. Yeah, so just this is an online tool, if you don't know, which is called Godbolt, which allows you to very easily write some C++ and get the assembly. It's very nice if you want to look at the impact of different compiler settings, different compiler versions as well. So let's try to understand better what the CPU is actually doing. So as we see, there is a stream of instructions, and we can have jumps which take us in other places, but basically we have instructions that we need to execute one after the other. So a simple way to consider this is you have a black box, you give an instruction in, it gives you result. By result, it means it actually changes the state of the machine. But this is not, it does it in a more sophisticated way. So the first thing is that it does a pipelining, which means that it's got multiple parts of the chip doing different things. So a standard pipeline in CPU is that first you're going to fetch instruction from memory, then you're going to decode this instruction, trying to understand what the instruction actually means, what it does. Then you execute the instruction, you can see my pointer, yeah, so execute the instruction, and then you will write back the results to memory. So that's what you can have, of course, that's just a standard pipeline, but you can have all kinds of different pipelines. But so they will be handled by different parts of the chip, and what it means is that all parts of the chip can actually work in parallel, right? There's no reason why one part of the chip is busy, the other part of the chip cannot do work. So given that you have a stream of instructions, so first you have your first instruction, which is as the first fetch stage, but as you get the second one, you can do the fetch of the instruction at the same time as you're doing the decoding of the previous instructions. And of course, as you add more instruction, eventually you fill the pipeline, and when the pipeline is full, every new step, you will regenerate a result until your pipeline is empty. So that's a very efficient way. So of course, the first one, it took us 4 steps to get the result, but once it was full, we get it. So what is important is to make sure that we can maintain this property of the CPU. So when there is a jump, if the CPU does not know where it goes, it cannot prefetch the next instruction, right? Because if we have the jump that says a cyan color, we don't know what is the next instruction we can't. So it tries to figure out what the next instruction is going to be so that it can have it in the pipeline as well. But what happens actually is that this is even more complicated, that it is superscalar, and it will fetch a block of instruction in one go and do the first fetch and decode step, and then it will dispatch to various different units, so there's a unit doing the arithmetic with integers, a unit doing the floating point, a unit doing the memory access, might be a special unit for special types of instructions, for reordering things within a register and all that kind of stuff, and all of these units have their own pipeline. Which might be more or less long, and they might retire in memory at different times. So you have something which is more like this. So I don't have the animation, but you can understand that so you can have redundancy as well, right? So stuff gets here, and you can be dispatched, depending on what is available, you can be dispatched here, and some they're actually called ports. Some of the ports might have more capacities than others. And so I have an actual image of what this looks like. So this is an image from Intel. This is the Sandy Bridge architecture, which is an architecture from 2011. So it's a bit old, but it is still the best performing microarchitecture from Intel for single core performance. And so you can see it as, well, of course, it is more sophisticated, but you have something of the same still. So you have a main pipeline which takes the instructions in, decodes them, and then they will be scheduled on a number of different ports, and all of the ports have different units which can do different things. So the arithmetic logic unit is doing basic operations plus multiply on integers. You have vector units operating on special stuff we'll see later. Some ports do memory access. And so, yeah, depending, and you can see we have redundancy, right? So we have multiple LUs. Yes, there are 3 LUs. So that means that you can do three multiplication at the same time. And the reason you can do 3 multiplication at the same time is also because the multiplication has a latency of 3. So this way, if you fully if you give enough work to the system, you can completely hide the latency of the multiplication. So yeah, this is a very complicated system, but it's got that thing. And one interesting aspect as well is this thing out of order. It might actually reorder your operations to guarantee that the pipeline can always be filled, because there might be dependencies on the operations, and the dependencies might force you to wait. So we'll talk about that in the next slide. Yes. So let's imagine this situation. My load and store operations detect 3 cycles before the result is accessible. So the store is not very important in that example. The load is more important. So I load from memory. I will only be able to use the result in 3 cycles. So in the other 2 cycles that I have left after I have scheduled the instruction, I could do something else. So if I take this example, this code, which does it loads a value, it adds 2 to it, and it loads another value, it adds 2 to that value as well. So every time we want to add here, we will depend on R1, but R1 is only available in 3 cycles. So we have to wait 2 cycles, which are wasted, before we can do the add. And same again here, and then same again here. So if you reorder stuff, you avoid this problem, because you do a load, you do another load which doesn't depend on it, another load doesn't depend, then you have the add, but this time it's been 3 cycles since we did this load, and we don't have to wait. So what is this called? So on the hardware level, they call this a bubble, because the way this scheduling, the agencing of the pipeline works, the event is called a bubble, but in the software world, it's usually called a stall. And this is something very important, that if you can identify it and find you have a stall in a critical part of your program, that's a good indication that you should try to figure out a different way to order your instructions to avoid this. So the CPU, of course, being smart, will already do this transformation. It will do it with a window, so that it will only reorder things, it will only look ahead a certain number of instructions, so it is limited, but it will already do this kind of transformation for you, so that's because in practice, a lot of this is very dynamic, and so doing it at runtime as the instructions are executed is a better way of optimizing it. What else? Oh, I have this screen, I should use this. So as I said, there are different types of ports with different types of instructions, so which do different things, and the different things each have different speeds and different redundancies. You can have only one, maybe there's only one unit that does a specific type of operation. So that means depending on the type of operation you're doing, they don't all have the same cost. It's not the same as doing an operation on an LU, you can see, which is quite replicated in doing an operation on a floating point unit, or like a division, which already is an expensive operation, but you only usually could have one unit to do that. And so, as I said, the port will be dynamically allocated, and they all have, each unit is pipelined itself. So, on some processors, like mostly embedded or old processors, everything was executed in order, but the CPUs do out of order. And this is a problem, the out of order execution, when you're doing concurrency. Because if you're doing out of order, that means that the results will be committed to memory at a different time than you expected. It might not be consistent with what the program might suggest. And so when you have multiple cores accessing the same memory, they might end up with inconsistent state. And so the way to work with concurrency, of course, you can use very high-level concurrency concepts like mutexes and all that. But if you're trying to work with atomic instructions, even the atomicity is not enough for you to make sure that your program is well-defined because of this reordering that happens. And so there is a way to enforce on most architectures, which is called a memory fence, which will enforce that no reordering can happen beyond this point. And of doing that means that you limit the capacities of the CPU to optimize your code and better fill the pipeline and the superscalar resources. But it means that you have you can make your code work better in a concurrent environment. So you have to take that into account when you're doing, if you're doing lock-free programming kind of stuff. Bear in mind that this is why it will slow down your computer. Even if everything looks like it's atomic and magic, you will still slow down because of reordering barriers. Yeah, so the different types of memory models where you can do more advanced memory reordering. So x86 is quite conservative, so as to not break too many programs, but some architectures are a bit more crazy in the reordering they're doing, which means they can better utilize their resources, but they make it more difficult to make concurrent programs. So as I said, it's quite important to avoid stalls, especially since we have CPUs tend to get larger, deeper and deeper pipelines. So if you have a stall, you will end up paying the full latency of an instruction. So there are some tools which can identify that. Performance counters from the hardware, which can be accessed by perf, for example, can help you identify stalls. The Intel vTune has a nice tool to identify stalls as well. So that's one way. Okay, so as I said, not all instructions are equal. So it's a good idea to remember that you have a good idea for which instructions are faster. And so there are, of course, some optimization you can do, trying to make use of that fact. And there are a number of special instructions which might not be directly accessible if you program in C++, but part of the hardware is dedicated to do some special operations. And so it's interesting if you're in a domain that where you can make use of it, to be aware of it and to use them. So the relative instruction speed, so this is just a rough list from fastest to slowest. Of course, it very depends on your hardware, it depends on your situation. So the speed, there's the latency aspect, but if you're doing many times the same operation, it will be pipelined. So you would not get the same speed if you're doing just one operation on its own, and if you're doing many of them. So the tests, like comparing integers, comparing floating point is more expensive. Bitwise operations are cheap. Adding is very cheap. Multiplication it's still cheap but more expensive than addition. Floating point multiplication, and then you end up in the realm of slow stuff when you're dividing. So, to give you an idea, so a floating point addition might be 1 cycle, but a floating point division would be 20 cycles of latency, and integer division maybe 40 cycles. But your millage may vary, and some people have complained to me about this to say that the list does not reflect what their experience is. This is something I came up with, and so some Unrolling on the school has use similar list. So if you want to know, there are Agnefog, a guy on the internet. He has a table with all the for each microarchitecture, what is the latency and the expected throughput if everything is pipelined, so you can know the actual details. So one thing which is often completely not used in the hardware, it's used by the compiler but not used by software developers, is SIMD. So the idea of SIMD is you will apply the same instructions on multiple streams of data, multiple lanes, as we call them. And so the way it works is it works at the register level. Instead of having a 32-bit or 64-bit register, you have a 128-bit register which contains 4 values of 32-bit each. And it can, in one cycle, for example, do an addition on each 4 of the values. So it can speed up your computation by a factor of 4, for example. So it is mostly used for floating point, but you can also use it for integers depending on which architecture you target. So on x86 SSC2 has integers, so 128-bit registers, and can deal with all kinds of 8-bit, 16-bit, 32-bit, and a little bit 64-bit integers. And AVX2, which is a more modern thing that Intel has released, which is since as well microarchitecture, is twice as big. So just to be clear on what SIMD is, so it's not some kind of threading model or anything like that. It doesn't use threads. It doesn't involve the operating system. It is different instructions and different registers. So this is the same code. Well, not the same code, but code that does the same thing. I think that's, yeah, there must be a sum. Yes, this is a sum of 16-bit integers, but promoted through 32-bit. And so what differs is that when you're doing normal scalar values, you're using the general purpose registers. So those are the general purpose registers, the 32-bit registers on x86. And you're doing an add instruction. But when you're doing it with SSC, you're using those special XMM registers, which are 128-bit. And you're doing this PAD, don't remember exactly what they stand for, the D, which does, that's a 32-bit, it does 4. There are 2 of them because it does, it does 2 times for each instruction, that's 4 additions. It does 8 of them because it's loaded through, well, we'll see more of the code later. We'll explain this unpack and things. So yeah, this is what I want to make clear is this is inside the CPU. This is not a software thing. So this was inside the chip, but there's plenty of stuff happening outside the chip as well. So the first thing being multithreading. So they are, well, still inside the chip. You have multiple cores, but you can be generalized to multi-socket systems. You have the way multithreading was first implemented is that there's time slicing. So you have multiple processes you want to run on the same core. So that means that each process gets a slice of the time on the core, and you swap between them. Something which was first made is that, so I'm already getting confused, sorry. Yeah, so this is hyperthreading. SMT, synchronous multithreading. I don't remember what the acronym stands for, but this is what is known as hyperthreading on Intel processors. And the idea is that if you have multiple threads running on the multiple thread of execution, you want to run on the same chip. Since this chip is already is multiscalar, it has multiple units which can run in parallel. So you could feed the different ports from multiple threads. So this is the first optimization that people have thought of before. So this only needs a single core, but on the single core, you can, for multiple threads, you can feed this as we distribute inside this thing. You can say one thread will use part of the core, and another thread will use part of the core. If you like, one thread is doing an RU, the other one is doing another RU, you can still map the multi-threading, the different threads to that. So this is SMT. So SMT is personally bad for the kind of thing that I do, because what I do is I want to make sure that each core gets the maximum speed it can get. And it will mess up with other reordering that the CPU is doing, because those resources will be used by other threads. So it cannot be used from the same thread. So if you want maximum single thread performance, you want to disable this feature. But if you want maximum system utilization, because you care more about throughput, you should enable this feature. So SMP, which is you have multiple cores, multiple sockets, which gets extended to NUMA, non-uniform memory access, when you have multiple sockets, multiple chips, but they all have their own memory bank. So they can access the memory bank of the other one, but it's more expensive for them to do so. So what is interesting about this thing, so it means multiple threads can run on different cores, and they can be moved around the different cores and different CPUs of the system. But they will have a different cost to accessing different parts of the memory, so you want to take attention of all the different threads are actually scheduled on the machine and make sure that the memory you work with is local. So this is an image. I don't know if you can see it very well because it's a bit small, but this is an image you get with a tool called LSTopo, which is part of the HWLock library. This is a command line tool with the library, which builds you a pretty graph of what your architecture is. And this shows you an example of a NUMA architecture. So what we have here is we have two sockets. They all have their own memory. So this is 24 gigs on each socket. And each of those sockets, of course, there is a cache, the L3 cache, which is shared across all cores inside that socket. So, of course, each socket has its own cache. And then each core has two levels of cache. We'll talk a bit more cache later, of course, but and inside the core, this is representing hyperthreading SMT. You have possibly two logical processing units. But if this core and this processing unit and this processing unit will be very easy for them to communicate with each other, but if this wants to communicate with this, it has to pay much higher penalty. So there's a smaller penalty if it's close. So it's important to think of the system as hierarchical and make sure that if you have some tasks that need to talk to each other, you must pay attention to scheduling. And one other aspect which is not on that picture is that this is connected to the node will be connected to a given, they will each have their own bus. And you might have devices on that bus. So you might have a network card, for example. And so if you want access to your network to be as quick as possible, you better make sure you schedule your threads on the same node where the network card actually is. It will make a very big difference. How does it work because we see that there are two types two parts of the memory on each NUMA node. How does it work in the system which sees the memory as a global thing? So the way it works is that it allocates on most systems, on Linux especially, on first touch. So the first time you touch a page of memory, it will allocate that page on the node you're actually running. So one common anti-pattern is that you first initialize everything to 0, and then you distribute it to multiple cores to work with. But that's already broke everything, because it means you have bound the memory to the master. And you want to make sure that each slave, if you're doing a kind of master-slave or fork-join model, each slave has its own copy of the memory, which is bound to the specific part of the hardware it's working on. Yes, that's it. Context switches. So, of course, when you're running multiple threads on the same core, you need to context switch. Context switch is potentially expensive. So we're talking about 1,000 cycles. And every time you go to the kernel, you're causing a context switch. So there are a few techniques like a VDSO, which is a way for the kernel to expose information to user land without going through the when doing a system call. But so if you need something very low latency, you want to avoid all the context switches, because this is an expensive operation. But of course, if you have more work and you have CPUs and you need to share resources, context switches will be necessary to some degree. So here I'm talking a little bit as well on force sharing. So as we saw in this picture, the L3 cache is shared across all these cores. And so if you have multiple cores which write to the same location, or read and write to the same location, when this one writes to the location, it will cause the cache line to be evicted from memory, and this will conflict with. This means that the other core, which is getting that cache line, might need to get it from memory again instead of using from the cache. So you need to be careful to make sure that the cache lines that each core is working on do not collide, do not overlap. So we'll discuss, but I'll show an example a bit more later. Okay, so let's talk more about caches. So why do we have caches in the first place? So RAM is DRAM, but DRAM uses less registers, but it is not as fast, essentially, because it needs to be, well, I don't know exactly the specifics, to be honest. It's more circuits and electronics. But they have different technologies for this. And so DRAM, of course, using less register is more dense. So you can have larger of it, and it's more expensive to have SRAM. So you have multiple levels, typically. The first level, the first two levels are normally inside the core. They will be fairly fast. Of course, the first level being faster. This is an estimate of the cost you would pay when you reach from the cache. And so when you start going to level 3, it's starting to be seriously more expensive. And when you start, so EDRAM, some experimental processors have this kind of stuff. This is an embedded DRAM inside the chip. And so main memory, that's about 300 cycles. And NUMA is highly variable depending on the kind of bus and technology you're using. So I think we can make a pretty good statement. We should try to get stuff inside those whenever possible. Make sure that the stuff we're going to access is within those two levels. So I have just a small picture to explain exactly what a cache is and how it works. So we'll just, it's a toy example, very simplified. We'll assume that the cache contains the latest 2 lines that were accessed. So that means initially my cache is empty, I have nothing in the cache. But I make an access to a location, the location being the bright red spot. And when I do this, what actually happens is that the whole line is put into the cache. So this is considered a cache miss because it was not in the cache, I need to fetch it from memory. Then I access another location, but this is a cache hit. I put the whole line into the cache, so I have it in the cache, I don't need to fetch it from memory. So the first time I had to pay the penalty of getting it from the cache, but now I get it from memory, but now I have it in the cache, I don't need to do so. And then I access another location, this is not in the cache, same problem again. And I access another location, it's not in the cache, same problem again, but since I can only contain the last 2 lines because my cache is of limited size, it means I need to evict the old line. And if I were to access the same location again that I accessed here or here, I would need to pay again for the price. So we can deduce, well, we can go back to that later. We can deduce 2 things. So we need to take into account spatial locality and temporal locality. So temporal locality, I only can have a certain amount of lines inside my cache. So I need to make sure that if I need to reuse something, I better do it soon rather than later. And the spatial locality, when I get a cache line, I get get everything which is within that line, not just one single value. So if I can put all the stuff that I need inside one cache line, I have that many less cache misses. So in practice, the system I explained is very the toy example, but it is more sophisticated. You have the mapping between the memory and the cache is not a simple FIFO. It's actually a given location, multiple locations of memory can be mapped to the same location in the cache. So you can be, so when you load two different addresses, they can end up evicting each other. This is done to minimize the amount of circuitry needed to make this work. Okay, so as we said, it's good to have compact objects. So mostly if you care about latency, this is a very important thing. You want out of your hot objects you're going to need to fetch from memory very quickly. If you need multiple bits of it, you want to make sure that everything fits inside a single cache line or as few cache lines as possible. Also make sure you align on the cache boundary, because the memory is organized in cache lines, but you might have your objects might be overlapping two cache lines. That means you need to do two loads anyway. So if you really care about the hotness of your object, you want to align. And of course, you want to SBO kind of optimization, where you store the string with itself, means that you store instead of first getting a pointer and getting another data which is pointed to, you can get everything inside one go. It's better. Okay, so probably need to speed up because I have many more slides. So of course, if you're doing C or C++, you need to be careful of padding because it's wasted space. So if you can reorder your fields, you will get better utilization of memory. And last thing to talk about the hardware is branch prediction. So as we saw earlier in the very first thing, there's a first pipeline of the processor which needs to know what is the next instruction being executed. But when you have a conditional branch, the CPU does not know where you're going to jump. So it's the same problem if you have a virtual function call, because if you have a normal function call, you know the addresses, you know where you're going to go. If you have a virtual function call, it's a lookup inside a table, so you don't know where you're going to go. So to minimize this problem, CPUs try to predict, to guess where you are. And if you predicted it right, all is good. There's no penalty. It's as if you had a continuous stream of instructions. It predicted wrong. Well, you have to pay a lot of well, you waste, your pipeline gets stalled. So the first thing, so yeah, what's this one I'm saying? So what happens if we took the right prediction? There's no latency penalties actually, so it is faster that if you're doing branchless techniques, you try to avoid the penalties of jumps, are not as fast as a well-predicted branch. And yeah, so it can be, but if you're badly predicted, it can be very expensive. So branchless code, there are techniques to do that. It's a good idea to use it if you do not know at all. You have no way of knowing which side of the is going to be, which if your condition is going to be true or false. So you're going to execute both options and somehow combine using bit tricks, stuff like that, to get the final result. And so usually the two options you can combine, you can do them in parallel with a superscalar processor, so it's not too much of a concern. You will be limited by the most expensive of the cases, but if the two cases are just the same cost, it is a nice, possibly a nice optimization. And so we'll talk a bit about this SIMD later. And if you're doing, if you want to use a special SIMD instruction to actually work with 4 or 8 values at the same time, you need to do this anyway because there's no concept of branches and jobs. So what do I have there? Yeah, so static branch prediction. So how does the prediction actually work? How does it decide whether the branch should be taken or not? So the initial guess, given that we don't know, we have no other information to know, is called static branch prediction. So this is something which was Intel documented it, that they implemented it in Pentium, like Pentium 2 processors. But it's not clear whether they still actually do this as an initial guess inside the processors today. But this is still a heuristic, an interesting heuristic for the cold state. So the idea being that if you're doing a loop, you can say that the loop is probably going to be taken because no one does, well, people do loop with one iteration, but typically there's more than that. So you can suppose that when you do a loop, it's going to loop again. And when you're doing a branch, it is often a special case. And so you can assume that it is probably not going to be taken because this is like just a special value in the realm of all possible values. And it does this based on whether the relative jump is a jump forward or a jump backward, because a loop, as we saw at the very beginning, at the assembly example, I can maybe go back to that very quickly. No, it's not it. Oh, that's very far away. Yes, so when we do a loop, the loop is translated into a jump at the end. So the jump here jumps to a location which is before, so we can, so the initial guess can be, okay, this will be taken. But here we do a jump forward, right? So this is only for a special case, which we assume that it's not going to happen. So the initial static branch prediction would say this is not taken, and this is taken. And so this means that it will prepare in the pipeline the execution, assuming that this branch is as is. Okay, let's go back. Yes, that's static branch prediction. But what is actually more useful for a normal program after the cold state? So this is useful if you have no history information, but otherwise it will use history. So based on history, if statistically in the past this branch has been taken many times, well, we can predict that this is going to be taken again. And if it hasn't been taken, we can predict it probably will not be taken again. And so that's very important, because it means that the compiler will optimize for control flows that happen often. But in some programs, you want to optimize for things that don't happen very often, and that's actually quite difficult to do. You need to trick the compiler and trick the CPU into optimizing for cases which are very rare, which is a case of applications I work on. Because trading decisions, you will receive thousands, tens of thousands of things of packets, but only very rarely you will react to it and emit an order. But when you do so, it needs to be very fast. But everything will be cold, and you need to maintain it hot. And so it's using some cache system, a bit similar to memory caches, but it's less clear. I don't have full understanding of exactly it works, but it will store a certain amount of previous states, and based on that, deduce. Like there is a repeating pattern, that's the same pattern will be repeated again and again. So what can we take away from that? So this was the overview of the CPU works. So the hardware is smart, but sometimes we can build software which prevents it from doing what it needs to do. So we try to make sure that we write software in a way that we can maximize the smart optimization it is doing. In terms of parallelism, there's very hierarchical parallelism. So if you have a NUMA, inside you have a SMP, normal shell memory, and you have inside you have hyperthreading, you need to take into account those effects if you want to have a large-scale parallel program. Different instruction, different speed, but the most important thing is really memory. So memory is quite slow, and you want to make sure that whenever you access memory, this is as fast as possible. Okay, so let's look at what we can do from a software point of view to make things better. So one first thing that the compiler does, but that you might assist as a software developer, is inlining. So when you call a function, there is some extra overhead. You need to pass stuff on the stack, and different ABIs might require you to do different things. And the function has very limited knowledge as well of what the input is. So it needs to assume that it is very generic input. And of course, you have the aspect that you jump to another address, even if the address is well-known and it can be fetched in advance. It might be in another page, in another location, and you might have some TLB, which is well, for page management, is something for page management. So the solution is to expand the function. So it's very classical things, but you need to be careful that you will increase the size of your program significantly. So just one word about ABI and cost. This is a problem I encountered while writing a library for making easier to use SSC instructions. So of course, this is not something you can read very well, but the idea is to show you that there's a lot of crap being generated. So this is on 32-bit. So the ABI on 32-bit on x86 is not the same as in 64-bit. And the type that you get for SCC2 when you're doing integers is M128I, and it's the same regardless of whether you're doing 8 bits, 16 bits, 32 bits, 64 bits, you use the same register type. But if you're doing some kind of C++, more high-level library, you might want to wrap that into a richer type, which would then be different for 32-bit, 64-bit. So you wrap it into a struct like this, called this v4i, because it's a vector of 4 32-bit integers. And so we'll compare here. So I do a simple function that takes the struct by value and does addition or multiplication of each of the underlying members of the vector. So there are two variants, just one which is forced to prevent inlining to see what happens. And we're going to do an add mul function that calls those two functions. And so we can already see that the add and the mul, they need to get their inputs from memory, which is a bit of a shame because this SIMD is very good when you keep everything into registers. So you pay some extra overhead here because you go through the stack. And when you, this is a version which is not, which is inlined. So because it is inlined, it was able to remove most of those accesses through the stack because it propagated them and it figured out that it was the same value. But when you don't actually inline stuff, in the second case, you will be going through memory many times, and the code which is generated is actually bigger than the sum of the inline code plus the other two. So this is not the compiler decided to, if that happens to you, the compiler might decide not to inline because it thinks it would generate too much code, but in practice there is so much overhead by the ABI cost that it would have been better to inline. So just for comparison, this is what happens in 64-bit, which is, of course, much nicer because the ABI says that any struct which is of the right size will go through registers, so you don't have this stack dancing phenomenon. So another optimization you can do is specialized stuff. So this is something C++ templates are very good at, but sometimes we want very generic code, and because it needs to deal with all sorts of cases, it is very slow. But if you make specialized versions of your code for very specific use cases, you will be able to make it much faster. The problem of doing this is that instead of having one bit of code, you're going to have many versions. That means more code, more pressure on the instruction cache. Also, you might need to use metaprogramming or generating techniques to do that, which is a bit of overhead. So inlining already gives you some of that because when you inline, it will specialize this particular call for the inputs you're giving. Other use cases when you want to do this is when you're doing some things where the size varies greatly, the type of things you can do. So I've experimented myself writing a fast Fourier transform algorithm, which using metaprogramming techniques to generate an optimized fast Fourier transform for specific sizes, and then it still works with a runtime value. It just picks the best one, based on the switch, and it made a very significant difference because that means that you will be using the same instructions. You would not need to do as many tests inside the core loop. You'll be able to more easily have something which just does the same thing everywhere. So of course, static types, So dynamic languages, they have these boxed types, which everything is a pointer, which is very expensive. The obvious stuff, like it's better, you want to move the branches out of your loops. So this is, of course, there's a compromise to be found. Do you want a very generic version? Do you want the specific ones? But always, if you want optimization, the first thing to do is to try to identify what is special about your case and saying what you can do for that case to make it better. And the CPU is better at doing, if you choose first what it is you want to do and then do that thing without thinking too much and having to every step of the way figure out what it is you need to do. So data access patterns. So one first optimization is scalar promotion. So we said that memory access is expensive. Every time you access memory, even if it is in the cache, it is more expensive. It is in registers. And if it's not in the first cache, in the second level, it's still more expensive. You want to remove them if possible. And compilers are limited in what they can do because they have limited knowledge of what your program actually does. So one first optimization is that you can explicitly load stuff into variables. So that makes your code much more verbose, more explicit, but it makes sure that there are no loads that you did not expect to happen to be in the code. So one example is the aliasing problems when you were working with pointers or references. So in the first case, there is the code generated by the compiler will most likely be penalized because it does not know that, well, at least we don't know even when you look at the code, right? But you would think that size and value are never part of the array. They are completely different variables that live elsewhere. And they should stay constant during the program, right? But since there are references, they might actually alias with the array. There might actually be elements of the array. So every time we modify and position the array, we might have actually modified size and value. And so the compiler will need, every time you reference value and size, to reload them from memory. If instead you took size and value by value, or if you just make a new variable, so this makes an explicit here. This makes an explicit load from memory. We load size into a local variable SZ, and this makes it explicit that this and this stays constant within the loop, and that there is no need to load it again.
If you didn't pass it by reference, because it's
yes, if you pass it by value, you would have the same effect. So another optimization is unrolling. So typically in a loop, you do something, then you compare whether you should end the loop. If you do not end the loop, you jump and you start again. And so that means every time I do an operation, I do a comparison, and then possibly I jump. It's better if I were to do, let's say I do 4 iterations of my loop, and then I compare, well, am I at the end of the loop yet? So this is basically this optimization is called unrolling, and it enables a variety of many other optimizations. So you can also do that sort of stuff because basically it makes your code more verbose, right? So let's say you want to overload by a factor of 4. So of course your size is not necessarily a multiple of 4, so you need to have an epilogue at the end to end up with trailing data. What I do is just a function f of I, and I have overload by 4. I could call my function f 4 times. But you could build something in C++ using templates that does it automatically if you wanted to do that. That's not very difficult. I don't have the code, but it is very simple. So now we're looking at more advanced optimization you can do. So we saw that it's good if we can pipeline stuff, but if there is dependency between each operation, well, you cannot advance the program because you need the previous result. So you need to wait, and this causes problems. So a way to do this is to organize things in different batches, and that the second step can run in parallel with the first step, so long as the second step was the first step as one step ahead, essentially. But so because of that, you might have higher memory requirements and things like that. But so this kind of optimization can work with instruction, but it can work with very expensive functions as well. So say I have an example here. I want to do some computation on an accelerator, on a special device. It can be a GPU, for example, but my data is on my CPU, and I want to send the data to the accelerator, do the computation there, and send back the result. And this is not the optimal solution because most likely I can transmit data, because I need to wait until I've transmitted the data before I can start the computation. And transmitting the data, if it's a big amount of data, it can take some time. But I can, if I process it in chunks, I should be able to do it in parallel. So a pipeline solution will divide it into blocks. First, I send the block 0, and at the same time, I can process block 0 and send the next block. And so typically, depending on the kind of bus you're working with, you might not be able to do send and receive at the same time, but you can at least have one I/O operation and the processing at the same time. And you will need to make sure that the size you choose for your block is the right size so that it can overlap the computation and you don't end up waiting. So then we will look more in the context of a loop. So let's say I have a loop. All iterations are independent, but within one iteration, I have a chain of operations. And of course, there's dependency B. I need to do A before I can do B, and I need B before I can do C and D. So we can be like a pipeline we saw earlier. So A can do a load, B does a add, and D does a store, or I don't know what C would do, some other operation. But it can be something much more, because we're in the software world, it can be very large parts of your application. I don't know if you're doing video processing. Let's say for some reason you're working frame by frame, and you can you have multiple stages, and you can do the first stage. You can do so the last step can be on the first stage, while the previous steps are on the previous stage. But you'll see more with an example. So we'll assume that there are different latencies of the operation. So if we did it like we did the first example, we just unroll, and we make sure that we schedule operations like we did earlier. A has a latency of 3, so that means I can only start executing B 3 cycles after the dependent data has been done. And so all of these columns mean that these operations can be executed in parallel by the processor, or can be parallel because you use a special system, but you could also, if you have large functions, you could dispatch them to multiple threads if you wanted to. And so we see that we have to inline by a factor which is determined by the deepest latency of the worst operation by 6, right? And we have to use as well 6 registers to be able to do this. So if we had very deep operation, we might run out of registers because there's a limit. 16 registers is what you have. So that's for this case. And another technique is to do register rotation. So basically, you will first prime your data, and you will be running a normal loop, which only does each thing one at a time. It is not unrolled, but each of the steps is shifted by 1, except I shift. So to be able to overlap C, so C has a latency of 6, right? And so since I only have 1, 2, 4 steps, I cannot completely overlap it just by one set of all the steps. So I needed to do it twice. So it is. So we can see that's why we've got R0, R1. And I need to compute 2 of those because C is. Where is it exactly in the code? Yeah, I think R0, where is R1, R3, R4? Yeah, I'm getting a bit confused now because I wrote this like last weekend. But every step is just shifted by one, except one of them needs to be shifted by two to be able to overlap the latency. And what you get is actually, you get much tighter code, which it's the same. It will, you have four instructions that you can use in parallel. You can always add each instruction. And you possibly use a different number of registers. In this case, it's not better. But if you have many steps, you actually divide, you have the sum of the latency of each step divided by the number of steps minus one. So for deep pipelines and especially more software pipeline, if you're doing some image processing, you have to do different things. First, you detect the edges, and you do something else, and something else, something else. And you can pipeline this sort of process with this technique. Let's talk about caches and memory. So one technique, which is the most important technique when you're doing linear algebra or working with image processing, anything 2D or 3D, is tiling. So as we traverse large arrays, and we need to go back to certain values because we cross multiple dimensions together, this means that you need to make sure that when you go back to them, they're still in the cache. And the best way to achieve that is to simply cut your space in multiple smaller tiles, which you can try to tune so that they fit in the cache. But the optimal size of the tile is a bit difficult to find, so if you use linear algebra, some linear algebra libraries actually have some auto-tuning step at installation time, which will look at the processor, do some tests, and figure out what is the optimal size of the tile. You can also try to use based on the just the cache size, but there are some other effects which might prevent it from being optimal. So let's look at this with examples. So the basics. I have some two-dimensional array, and I am traversing. I want to all of the elements. I want to multiply by 2. So what is very important first is that I do it in the direction of the cache, because otherwise I will have many more cache misses. This is bad because the only difference, right, between those two examples is that those two loops were swapped. So this is much better, but this is bad because it means I will, if the memory is laid out, well, I have a picture later, but if the memory is laid out linearly, we want to linearly go through that memory to make every next step will already be in the cache. Yes?
Actually, this type of simple traversal...
Or you can just do it with a single loop, yeah.
No, it can be reordered by inputs.
Yeah, so all of the optimization I'm presenting are already done by compilers, but they will only be done in certain conditions, and sometimes it is useful to do it yourself. But yes, so especially recently, compilers now have there's a new work that has been done. There is a theoretical model to represent loop nests in multiple dimensions, which is based on I don't know what you say it in English, but not a polygon, but like a n-dimension, yeah, polyhedron. And this allows compilers to make a lot of progress in recognizing what the loop is traversing the memory space, and to better optimize and schedule the operations. But still, I think this is very basic stuff, and you need to get it right. You should not rely on the compiler to fix this for you. So the bad example I gave was going through the memory vertically, which is there's no practical reason why you would ever do this for any algorithm, because when you're accessing this, typically you will put the whole cache line, which might be here, into memory. So it's much better to do when you access this, and then you will process this because it's already in the cache. So you minimize your amount of cache miss. So this is a pattern which is very useful for element-wise operations. And so if you want to do a vertical reduction, so say you want to, I take this full column and I want to make the sum of the column. So if I were to process the column and just add this with this, with this, with this, with this, it will be a waste because when you access this, you have put the whole thing into memory. So it is better to process it like this. And so the tiles idea is you will usually cut it in the same amount of dimension that you have, And so the world tile, well, it's mostly for 2D, I guess. No, I can't see my laser anymore. Well, I don't think you can see it anyway. But the tiles, you have small little squares inside the big, small rectangles inside the big rectangle, and you can see that you can tune the size of the rectangle so that it fits into memory. So this is very useful for stencils. For example, the stencil is something that will look at the points around a given point. It will apply an operation on all points, but it will look at the context. And so clearly we can see that if we need to access the value below and the value on top, we want those values to still be in the cache, and we need to organize ordering of our traversal for this. So this is for memory. So I think I don't think I put it, but yeah. So I have another presentation where I have a full details on some of these algorithms and how you make sure that they work properly with multi-core and SIMD and cache friendly. The instruction cache. So the instruction cache is something that few people care about because if you write most of the performance-sensitive code that people try to optimize are small loops, well, relatively small, condensed, a few hundred lines, a loop, and it will just reuse the same code again and again. But if you have much more complicated code and your need for performance is more dispersed inside the code, you care more about the cost of just fetching the instruction from memory. And to do that, you care about the instruction cache. So the same way instructions are in memory, they go to a specific cache. And it is better if you have small, tight code because it means that uses large cache is more likely to be in the same cache line. But of course, the more tight it is, the less you can optimize with unrolling and that kind of stuff that we saw before. So it's a compromise to find depending on what you want to optimize for. Sometimes we have a lot in our code. There is a part which is like dealing with very special cases, but it's in the middle of things that deals with very general cases. So you're wasting space in your instruction cache by things that do not happen very rarely and you don't really care about. And so what you should do if you care about this kind of problem is that you should group together in memory the pieces of the code that are hot, that really run, that most of your when execution that actually gets the instruction that get executed should be close together, and the instruction that don't get executed should be possibly far away to not distract from your code. So I have an example with exceptions. So and again, I have a screenshot with assembly that you can't see if you're in the back and probably not even in the front. But let's say I'm doing, we not consider whether this is a good idea or not, but I'm doing a function that divides and it compares if the second value is 0, and if it is 0, it throws an exception. But I'm not worried about whether that's a good idea to throw an exception. I'm worried about the quality of the code gen for that case. So clearly, dividing by 0 and an exception, this is something which we don't really expect to happen very often. This is not something we want to optimize a function for. The function should be optimized for valid inputs, non-zero. And this is the code gen that you get. So you can't see that code gen. I'm not going to walk you through it, but it is quite big because all the function does is divided A divided by B, but before a test, if B is 0, we throw an exception. But it is costly because I'm constructing a string, allocating memory, requesting memory from the system, copying the string inside the exception object, putting the exception object in the right place, setting up the tables or for stack unwinding or whatever. I don't really know how exceptions work, but this is costly. Now, if instead I did a function called doThrow, which does the same thing, it would do throw runtime error division by 0, or not even division by 0, it does just throw runtime error with the string I take. This is the code gen I get, which is much tighter because I pushed it to another function. And what I just get is I get my division here. I get my test. So the test is implied to not be very, very likely, so it's moved at the end of the function. and I do my division by, this is what would be predicated normally. And if I am in the case where I do need to throw an exception, I call to jump to another location, possibly far away. And so what I can do to make it even better, did I not do it here? No. So I'll put no return just to that doesn't know that the function does not return. But you can also tell the compiler to put the function in a special section, which means that each section will be completely separate. So they mean that the function will really be far away from your out function. So this is something interesting if you want to, have so little micro optimizations you can do to make better use of the instruction cache inside your typical programs. So let's talk about vectorization. So I presented SIMD shortly before. So we saw that this special vectors, special instruction that deal with many operations. But the problem is often, say, how do I use this inside my program? So I have an example of how you would use it for a sum. So compilers are supposed to automatically vectorize, but in practice they don't, because there are things in your code, either you didn't design your code to be vectorizable, so it still needs to be inherently vectorizable for the compiler to generate the right instructions, or it requires some transformation that the compiler is not very comfortable doing. And so if you want to do a sum with a vector, so a vector will do can do 4 additions at the same time instead of doing 1. But it will load the memory contiguously. So I mean, you will take the four inputs at the same time. So here I have an example. So this is my, I want to have a vector, contiguous vector memory. I want to sum, and I will be taking, I will remove, I will align stuff at the beginning and at the end, because so my vector might not be dividable by 4, and also it is better if I do align loads for vectorized instructions. So I will discard the very beginning and the very end. And by those packets of 4, I will multiply them. I will add them to each other. So that means that instead of doing the first element plus the second element plus the third element, I do the first element plus the fifth element, and at the same time the second element plus the sixth element. So it reorders the operations. And that's not a valid transformation in floating point, for example, unless you use fastmath and the compiler is free to make your completely break all your numerical code. You're not allowed to do this transformation on floating point. And integers, it's a bit of problematic because of promotion. People don't really think of this, but when you deal with 8-bit registers, you promote them to 32-bit, and those promotions make it more difficult for vectorization to occur. So if you do it explicitly, it's easier. So as we can see, we add this. At the end, we have 4 partial sums, which are sum of the part of the vectors. We still need to sum those up. So there's a special way to do that. And then we need to add it with the borders that we discarded at the beginning. So what does it look like? So this is hardware-specific stuff. It will allow you to, say, multiply by 4 the speed of your, possibly by 4 the speed of your computations. But this is the kind of thing you need to do, at least normally. Of course, there are libraries, we'll talk about that later, to improve this. But if you're doing, this is a sum of 16-bit integers. I'm just doing a sum and putting the result in the 32-bit. I want to do it with vectors. I need to use intrinsics. So intrinsics are essentially C functions which wrap a special instruction of the processor. But it is a bit verbose. So let's see exactly what happens. So I've removed the trailing data stuff so to make it simpler. So since I have 16-bit integers, and I have 128-bit registers for ACCU, I can fit 8 of them inside the register. So this is why the loop is unrolled by a factor of 8, because I will be processing 8 16-bit integers at a time. And the first thing I need to do is, I've got this 16-bit integers. I can add them together and get a 16-bit result, but that's very likely to overflow. So I need to promote them to 32-bit. So this is done by those unpack low and unpack high. So what it actually does is that it reorders elements and it until leaves with 0, which is which gives you a promotion for at least for unsigned integers. For signed integers, you will need to do either 0 or all ones, depending on the sign. And then I do a 2 32-bit additions on because I had a register with 8 16-bit integers, and when I promote, I end up with 2 registers, each 4 integers in them. I need to add them, and at the very end, I have my 4 integers, and I still need to perform some kind of a fold to get a scalar result. And there is an algorithm to do that, which is based on shuffling the elements around and adding all the values of each other. And you end up at the end with all the values of the vector being the same and being the sum. That takes log n steps, log by 2 steps of the cardinal of the vector, and you end up with the sum. So this will give you a speed up, but of course this is a bit involved. So I think, yes. So there are some efforts of C++ people writing libraries in C++, also on the C++ standards committee, to offer a more high-level solution to do that kind of stuff, so you can better address the hardware. So the current name in the standards committee is called DataPar, but it's very likely to change. So it represents SIMD vector register, but people wanted like data parallelism as a name because vector is already taken. And, yeah. And so it works with any size. So it will work. So as I said, this AVX technology is like SSC, but twice as wide. This library gives you the best size for your system. Of course, since we're doing promotion, we need to maintain consistency. So give me the best size for 16-bit, and then give me a vector which is twice as small for 32-bit. And so I load from the memory inside my 16-bit vector type. And then I have this cast thing, which is using new C++ 17 feature to get the low and high part when I cast it to my 32-bit vector type. And I just need to add the low and high part. And at the end of it, my result is 32-bit vector type, and I still need to fold it, which is just done by a generic lambda like this. So this is one way. So this is more like the intrinsic code I wrote, but another way is to just, you can also make the conversion happen at the load stage, but this depending on your architecture. So this loads into register 16-bit, and then convert that into 2 registers or 32-bit, and this directly loads and converts from 16-bit to 32-bit on load. Unfortunately, some architectures prefer the right one, some architectures prefer the left one, so Xeon Phi prefers the left one, and normal Xeon x86 prefers the right one. So there are libraries that do this. This is being targeted for the technical specification parallelism v2, which probably will be out at the same time as C++ 17, maybe. So there are libraries to do this. VC, Boost SIMD, I worked a little bit on Boost SIMD myself. But VC, the guy behind VC is the one leading the standardization efforts. So let's talk about how do I make good use of multi-core and that sort of stuff. So still keeping the sum example, let's say I want to sum a big array, and I've got 3 threads, or 3 cores. So of course, a normal system, you would get not such an odd number, but it fit nicely on the slide. So the way you do that is you just split into ranges, and then you have a binary tree of reduction. And this is not specific to the sum. What we're doing here can be done for dot product, for normal product, any kind of reduction operation. And so one important thing you might want to do, as I said, is to avoid fault sharing. I discussed fault sharing earlier. So you want to make sure that the size of the chunks you give to each core, the different chunks do not overlap on the same cache line. So the best way to do this is to align those chunks on cache line boundaries. So you would typically, so this is what the boundary is, right? But you would still give this one to this core. It would just do a bit more work, and the extra on the right to the blue core. But you need to make sure that the cutting point between red and green is on the cache line boundary to avoid that they mess up with each other work. And so then once you have done this and this, you can compute the sum. So this will give you one sum, this will give you one sum. You can do the sum of those two, and you get one sum. This will give you one sum, and you sum it with that. Right? So you can also you can advance at different speeds the system. So what happens if you want to do multi-core plus SIMD? So we can do the same algorithm we did earlier. So we 4x4, we add everything up, but we can do an optimization here. Is that the intermediate results will themselves be vector, and I only need to reduce to scalar at the very end of the computation. Okay. So what I want to say with this is parallelism is often you can be described as some skeletons, and so in the C++ 17, we have added the new parallelism.ts, which contains like a parallel STL, which contains some pattern that you can directly use. And this pattern I described is actually called reduce. And so you can just use reduce and pass some function objects. So currently reduce in the standard library does not do SIMD. That's going to arrive in the V2. But this is what it is going to look like. Currently, you can only do par, normal par, which is just parallel on multi-core. And so in this case, it would be an overloaded function object. So you generate, so you take the two cases. In overload is a function that generates a function object. We have both overloads constructed from the arguments. And so in the case of scalar inputs, you just add. In the case of data pair inputs, you promote to 32-bit and do an addition. And so this sort of skeleton is completely generic, and so you don't need to worry or do I deal with cache line boundaries, the trailings, epilogues, prologues. Everything is wrapped inside a function. So this is thinking in terms of those skeletons or reusable patterns is a big productivity boost. So this is with overloads, but you could also, in that case, just use a generic function. Because with polymorphic lambdas, you can just define one version for both. In literature, there are skeletons are something which is not specific to STL or C++. Many people think of parallelism in terms of certain patterns. And what's interesting with that is that it is well understood how you parallelize certain patterns on certain architectures. And so if you can translate your logic inside a combination of those patterns, you will be much easier to write efficient code. So you have transform, which is map, fold, was just same name, different names for the same thing, std reduce, and scan. So scan is the lesser known, it's the most powerful of the algorithms. It's similar to fold, but it doesn't give you a single input. It accumulates. What to explain? It's like a partial sum. If you have 1, 2, 3, 4, 5, it would do 1 plus 2, 1 plus 2 plus 3. So it accumulates like this. And there are also kind of skeletons which are more task-based. So you have like farms, pipelines, wavefronts, graphs of tasks, which will allow you to also make better use of parallel multi-core distributed systems using easy-to-use library features. So a lot of these projects are academic, but some of these ideas are being taken back into standard C++. Intel, TBB has made a pretty good as well, based on academic works that translated it into a pretty industry-grade library. OpenMP has some of that as well. So if you can think of in terms of that, you will be able to use parallelism much more easily. Yes, it's basically what I just said. And of course, something really nice is that if you can focus on the algorithm and let some kind of black box deal with the hardware-y parts, that's always some benefits because you can focus on your expertise and reuse some very good library that does it correctly. Yeah, so we're nearing the end of the talk. So one interesting topic is about if you're dealing with a sequence of elements which are structured, should you have a structure and a container of structures, and if your structures contain different values. So this is an example that someone gave me, but which might not be very easy to understand, I guess. So you just have a time series, and for each sample in the time series, you have a value, current portfolio values, and you have a current value for your external flow. And you can represent it like this, or you can represent it as I have a vector of portfolio values and a vector of external flows, each of them at a given sample time. And this is completely different layouts, and they're good at doing different things. So the SOA is much better if you want to use vector instructions, because you will be, all of the memory is contiguous of the same type, and you'll be able to just, so this is not vectorized here, but this loop is very easy to vectorize, because you can just take all the contiguous values next to each other, load it into a vector, and perform operations on them. But if it is AOS, you have a more variable memory layout. Not everything is not all portfolio values are next to each other in memory. You have gaps where the external flow is, so it's not as good. So it's a bit like if you have an image, you have RGB or RGBA image. You store each pixel at RGBA, so you have RGBA, 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 or you have RRR, GGGG, BBBB, AAA, and different layouts optimized for different things. So for throughput, you want SOA, but for latency, when you only care about the performance of treating one sample and not treating n sample, it's better if when I load the sample, I've got all the information I need in one load, and so AOS, area of structures, is better. So in terms of tooling and stuff like that, there are some solutions in C++ where you can give them, so usually AOS is the natural one, right? You can give them that layout and they will generate the other layout through metaprogramming techniques. It only really works for tuples, but with the addition soon probably of static reflection in C++, it'll be possible to generalize that sort of technique. Yes, question?
It's kind of unrelated to the slide, but does it make any difference from compilers and performance point of view as a micro-optimization? If you have the internals of the loop in SOA, to take the samples portfolio values outside of the loop as a separate const reference variable, and the same for external.
Yeah, so here you want to do some of the optimization we talked about, like scalar promotion, to avoid some redundant loads.
So
yeah.
From performance point of view, it would actually make sense.
Well, it depends. Does the compiler recognize then do the transformation for you, or does it not? And do you might have to do it. So, so the alias analysis in C++ is usually limited to types. So only pointers with the same types can alias each other. So not arbitrary pointers can alias each other. So they have to be the same type. So that limits a little bit. That gives more room for optimization. Well, I haven't really, this is just some code I picked up. I haven't really tried to build it. And so last part is a few techniques that you might want to take shortcuts in your computation by using specificities of the hardware. So usually additions are faster than multiplication, exponentiation, multiplication is faster than the power of something, and division is quite expensive as well. It's better to multiply. So a simple optimization you can do is when you see multiplication, you can think, can I translate this into additions? And this pattern is actually quite common when you deal with matrices, because the way people think of matrices, you have access at a position, at a given position, and so the matrix representation is contiguous into memory, but when you access, you're going to do a multiplication. So this multiplication is probably redundant in many computations. So yes, this is an example matrix type. So let's say someone writes a function to compute the identity matrix. So the identity matrix is zeros everywhere except on the diagonal, where it is 1. And so it goes through the matrix, and when the values are the same, puts 1, otherwise put 0. So this code actually would only work if width and height are the same, but yeah, it's an example code. But every time I do this access with this parenthesis operator, I'm actually doing a multiplication. So this is not the end of the word, right? But it can actually be avoided, and it does make a small difference to the computation. So this is code written differently, which directly doesn't use this operator, it directly accesses data. We linearized basically the access so that we only need to use additions. And so this will actually be faster. So I didn't do any benchmark for this talk, I'm sorry, but trust me. Something else, completely different aspect. Some operations, some mathematical operations are a bit expensive to compute, and you might want to use an approximation and refine the approximation. So it's a couple of functions that I gave that are so common that actually there are special instructions in the hardware to do it. And so the way you will refine is using the Newton-Raphson method. So let's say you have a way to find an initial guess for an operation, and you need to find a special function which is for which you will find the roots using Newton-Raphson. And so this formula will give you, based on a guess at some point, it will give you a better guess, and you can iterate until you're happy with the precision you get. So there are fairly common ones are the reciprocal and the inverse square root. So the inverse square root is particularly famous because of Quake3 and using this magic constant to generate an approximation of 1 on square root of x. And then you can refine by simply doing this operation. So I think Quake3 did one-step refinement. But depending on the precision you actually want your operation to have, you can do multiple steps. So they will still be faster than if you did use normal division and normal square roots, significantly faster. Well, I mean, it's still micro optimizations, right? Even though you're doing some multiplications and so there are special instructions to do multiplication and addition at the same time. So it's not that expensive. Also for floating point. And division, you have the same sort of thing. So like on Intel, you have a special instruction, RCP-SS, which gives you an estimate of the reciprocal. And so you can iterate 1, 2, 3 times, depending on, I think, yeah, 2 times might be enough to get the full precision for single precision. So yeah, so just if you you find that in your algorithm for some reason the division is apparently taking a lot of time, you might want to consider using this technique to speed up the division if you can take the hit of the less accuracy. And so in similar space, there are also mixed precision techniques that make use of the hardware. So on GPUs, in particular gamer GPUs, they're very fast for single precision, but they're not very good for double precision. But all scientific type computation, you usually need double precision to do on your data. And so you can use the single precision computation as an approximation of an initial guess. And then you can iterate and refine that. And this actually, it's not a topic I know very well, but I know some very famous people in the linear algebra world in academia did some research on it, and they gained a lot of performance by using this method. And so that's probably food for thought. It might be useful for other applications and need double precision. You can try get a first estimate with single precision. And the last thing is a little blurb on polynomials or polynomials. So let's say I'm French, so I use the word is the same, but not quite, so excuse me if I use weird words. So if you have a polynomial, you have a number of coefficients for each of the degrees. And a lot of functions will be evaluated by polynomials. Like if you want to evaluate the sinus, you actually what you do is you first find, do some kind of modulo operation to reduce the space to between minus pi on 4 to pi on 4, which is most expensive part of the process. And then you end up with a purely monotonic curve, and you approximate that curve with a polynomial. And so you can have a polynomial with many degrees to get the precision, or you can have multiple polynomials with smaller degrees, but you have multiple different intervals into which each of them is valid. And so you can compute all of them in parallel and see which one is best. But so polynomials are very important to approximate and compute some numerical functions. And so the optimal way, if you want to minimize the amount of operation, is called the Horner scheme, which simply factorizes the operation like this. And so FMA instructions are fuse multiply add, so that means R multiplied by X plus A3 and all that. And so very easily you can compute a polynomial. But we can see there is a problem here, that each of the operation depends on the result of the previous one. So that's not very good for pipelining reasons. So another scheme that exists is called S-string scheme. And it is less efficient in terms of computation. You have to do more operations, but you can do them in parallel. Part of the polynomial, you can see like the different factorization can be evaluated concurrently. But in practice, it only performs well for certain sizes. But if you have some polynomials, you might want to consider this, be it for interpolation as well, or all kinds of, for purely linear stuff, not interesting, but so long as you have 2, 3, 4 degrees, can be interesting to investigate, because of course it will depend on what other stuff you have going on your core as well. And that's about it for my presentation. I hope that I was mostly understandable.